Hello, everyone. Welcome back. Today, we'll learn about radians, arc length, and angular speed. So, our goals first, we'll learn about what radians are and also be able to group between degrees and radians. We'll be able to use what's called the arc length formula to find the arc length, radius of a circle under a central angle, depending on what we're given, and also be able to find the angular and or linear speed of an object moving in a circular path. We'll explain each of those. So first, let's talk about radians. So radians are another way to measure angles. So we're used to measuring angles with degrees. We also use what are called radians. And so this says a radian, if an object moves in a circular path through a central angle, so the length of the path is equal to the radius of the circle, that length of the path is 1 radian. Okay, let's go to the right and kind of explain that. Okay, let's say we have a circle. We have what's called a central angle, meaning an angle starting from the center of the circle. Okay, let's say this is our radius, r. And let's say we have this length, this angle theta. Okay, and let's say this distance here, which we'll learn we're going to call s in the future, this distance. If it's equal to r, the same length as r, then theta is equal to what's called 1 radian. The length of the path is 1 radian, and base of the angle theta is that radian. Okay, so the radian is the measure of that angle. And so we can actually then use radians to also measure angles. Okay, so let's take a look at how that works. So we know how, think about our x and y plane, how everything is divided up. Let's take a quick look at that. Okay, so this, of course, is 0 degrees, and it's also 0 radians, as you use RAD for radians. Okay. Now, this, of course, is 90 degrees, and as we'll see, this is going to be the same as pi over 2 radians. Okay. This is, of course, 180 degrees. And this is the same as pi radians. And of course, this is 270 degrees. And this is the same as 3 pi over 2 radians. And as also said over here on the right, you go all the way around a circle, it's 360 degrees. And that's the same as 2 pi radians. So it kind of starts from there. So if this is 2 pi radians all the way around, halfway around is half of that, or pi. Half of that then is pi over 2. Then essentially this 3/4 of the way around is 3 pi over 2 radians. So we can actually use radians then to measure angles just as well as we can degrees. And it's just a choice which you use. In some cases, though, applications, it's better to use radians. In some cases, we have to use radians. Okay, now, so one thing you want to learn and be familiar with is how to convert from one to the other. So first, let's practice with converting from degrees to radians. What we're familiar with into something new. All right, let's take a look at a few. So of course, already know our basic ones here. Okay, so 90 degrees is pi over 2, 180 degrees is pi, 270 is 3 pi over 2. Let's pick something else. Let's pick a basic one. How about 60 degrees? What is that? Well, the way we're going to do this, to convert from degrees to radians, what we do is use the fact what things are equal. Okay, and we actually could use any of these equivalencies, 360 and 2 pi. We're going to use or 90 degrees and pi over 2, for example. We're going to use this one, 180 degrees and pi. So it says to convert from degrees to radians, multiply by pi radians over 180 degrees. Okay, so the reason we're going to do that is we want our answer to be in radians. Okay, some people put the radians or not. Okay, and so we have a fraction that's going to be equal to 1. And so the reason we do pi over 180 is that we want our answer to be in radians, we want degrees to cancel out. Okay, and so this is equivalent. Pi is the same as 180. So this is 1. So we're not changing. It's like in multiplying a fraction by 1, multiplying a fraction by, say, like 5 over 5 gives you the same result, just a different form. That's what we're doing here. So pi and pi radians 180 degrees are the same. So multiply this across, and what this is going to be then, is this is being over 1 if you need to. So 60 pi over 180, okay? And then, of course, reduce. This will reduce. And actually, 60 goes into 183 times. It's going to be just pi over 3 radians. And sometimes people include the word radians or not, okay? So 60 degrees is the same thing as pi over 3 radians. And hopefully that makes sense, because 60 is 1/3 of 180 degrees. So we divide pi into 3 parts, then 60 would be pi over 3, okay? Let's look at another one. Let's do something like 220. Also, let's mention, if you want to approximate this, which you can, let's go to Desmos and approximate any of these. Depends on what you want to be given in. Now, actually do pi on here. All I have to do is type pi, pi, then divided by 3. And so that's approximately 1.05 radians. Okay, as a decimal. Now, let's do another one. Let's say, how about we do 225 degrees. Okay, the same thing. Multiply by pi over 180. Okay, degrees cancel out, multiply across, and so that's going to be 225 pi over 180 radians. Now we want to reduce, and I believe this one actually does. Let's see, yeah, this will reduce, and so that's going to be, I'm going to divide them both by 45. Divide both 180 and 225 by 45, and let's see, 225 by 45 is 5. So this is the same as 5 pi over 4 radians. Okay, that's the exact value. Now, if you want to approximate it, let's just go to Desmos or a graphing calculator. Let's do that. So type in 5 pi, so do 5, and just type letters pi, give you pi, divide it by 4, and you see we get approximately 3.93, decimal places, 3.93 radians. Okay. Let's do another one. Now, what if you have a larger angle, like a negative anything, a negative angle? Okay. Let's say you have negative 227.4 degrees. Do the same thing. Now, this one, we'll just do it in decimal form. Okay. Same thing, multiplied by pi radians over 180 degrees. Okay. And then let's just do this on Desmos. Negative 227.4 on your calculator, or as well. Negative 227.4 times pi, and divided by, not that, sorry, divided by 180. And that's approximately negative, this actually turns out, it was intending that, actually pretty close to that, but negative 3.97 radians. Just remember, so if you're going from degrees to radians, multiply by pi over 180. Simplify if you can, leave it exact, reduce your fractions if you can, or approximate it if that's what's required. Okay, now let's go the other way. Now, this time I want to convert from radians to degrees. Okay, so number 1, let's do pi over 4. As we'll see, this will be a very common angle. So what I'm going to do here then, the same way, we essentially want to use this equivalency, pi and 180, and we're just going to flip it the other way. Okay, multiply by 180 over pi, because what we want is, of course, we want our answer to be in degrees. And so to make it degrees, we need the radians to cancel out. Okay, I didn't write the word radians here, but assume that it says radians here and there. Basically multiply the other way, 180 over pi. Okay, here, pi is also cancel out. We have 180 over 4 degrees, and of course, that's just going to be 45 degrees. And hopefully that makes sense. Let's go back to our picture. If pi is the same as 180, divide 180 into 4 parts, gives you 45. Okay. All right. Number 2. Now, it's a little bit different. How about 3 pi over 17? So this is probably not going to be a common angle. We'll do the same thing. So 180 degrees over pi. Okay. Pi's cancel out. 180 times 3 is equal to 180 times 3 is equal to 540 over 17 degrees. And I doubt that comes out evenly. See, no. But if we approximate on the calculator, and I'll do 2 places, I'll do this on my calculator, that's going to be approximately 31.76 degrees. Okay. Now, what if we're given radians in something other than this doesn't involve pi, like say 5 radians? Okay, that's possible. So you can do the same thing. So times 180 over pi. Okay. And so that's simply going to be, nothing's really going to cancel out. And we think of this word radians here, but it doesn't matter. And so that's going to be 5 times 180, 900 over pi degrees. That's technically your exact answer, but that's not very useful, right? Let's find this on Desmos. So let's do 5 times 180 divided by pi. You can see it already gives us the answer. And so that's going to be approximately 286.47, 286.48, rather. So 286.48. Let's write it down here, have more space. 48 degrees. Okay. All right, let's do one more. Then, of course, we have something involving decimals. And also, you can notice there's this, a radian is a measurement of angles. You can have negative radians as well. Let's say we have negative 2.35 radians. Do exactly the same thing. Multiply it by 180 degrees over pi. This time, let's just do it all in the calculator. So let's just do that on Desmos. So negative 2.35 times 180 divided by pi. And you see the answer. So approximately negative 134.65 degrees. And of course, you can also then find a coterminal angle of that if you want. Okay, so that's how to convert back and forth of any radian, any degree. And actually, you can use these in real life. A good chance you won't have exactly nice values in pi. You probably have to do something more like the ones S2 we just did. Okay, now let's also think about the other understanding of angles we learned before. Let's find some that are find coterminal angles and supplementary angles. So let's do this. So what we do 3 pi over 4. No, change this. So let's do 4 pi over 6. Okay. 1. Find the complementary angle. So remember, complementary means if an angle is complementary, they add to 90 degrees. Okay. And 90 degrees is the same as pi over 2. Okay. So let's make a right angle. Okay. So a right angle here. And let's get 90 degrees is equal to pi over 2 radians. Okay. And so what we want to do then is, so this is equal to pi over 2 minus pi over 6. Only bad thing here is I put the fractions a bit. Okay. So remember, adding, subtracting fractions need a common denominator. And so to get a common denominator, you can always just multiply your denominators together. Or in this case, 2 goes into 6. What we're going to do is multiply the top and bottom of this by what we need to make this 6, which is 3. Okay. So pi over 2 times 3. Top and bottom, we need 2 times 3 to be 6. And of course, 3 over 3 is 1. We're not changing the meaning of this. Minus pi over 6. Okay. And so that's going to be 3 pi over 6 minus pi over 6. And so that's going to be 2 pi over 6, which is pi over wait, hang on. Yeah, 2 pi over 6, which is pi over 3. So what we have here is this one angle is pi over 6, and its complement is pi over 3. Okay. Now, let's also find the supplementary angle. Remember, supplementary angles are angles that add to 180. So here we have pi over 6. We want to find this angle here. Okay. So we're going to do that is remember that 180 degrees is equal to pi. And so that's going to be this angle is equal to pi minus pi over 6. Okay. Same thing. You need to put this as something over 6. And so multiply the top and bottom of this, pi over 1 times 6 over 6. That's going to be 6 pi over 6 minus pi over 6. And so that's going to be just 5 pi over 6, which you can't reduce. So this angle is 5 pi over 6. Okay, that's its supplementary angle. So doing the same thing we did before, except we're just doing it in terms of radians. So to find a complementary angle, subtract the angle from pi over 2, which is the same as 90 degrees. To find the supplementary angle, subtract the angle from pi, which is the same as 180 degrees. Okay. Now also we can find coterminal angles as well. So how about we find one positive and one negative coterminal angle. Okay, let's do the same thing once again for pi over 6. Pi over 6 is about right here. Okay, so the positive coterminal angle we just have to do, we're all the way around, is 360 degrees. That's the same as 2 pi. So it's going to be pi over 6 plus 2 pi. Okay, the same thing. We need to write this as something over 6. So multiply the top and bottom of this by 6. And so it's going to be pi over 6 plus 12 pi over 6. And that's going to be 13 pi over 6. So we start here and go all the way around and come back. That angle then is 13 pi over 6. That's a positive coterminal angle. Positive meaning it goes the positive direction. Okay. Now if we do a negative one, let's write the angle again. Okay. So here's pi over 6. And the negative is going the negative direction, starting the positive x-axis, going around here. Oops. And coming back, that's our negative one. And so, as you expect, then we subtract 360 degrees, or instead pi. So pi over 6 minus 2 pi is going to look just like this, except just a negative. So we have pi over 6 minus 12 pi over 6. And that's going to be minus 11 pi over 6. This angle here, we start with the positive x-axis, come back here and meet where this one is. That's going to be negative 11 pi over 6. Okay. And just like other coterminal angles, if we think about the trig values of these angles have the same, as long as they're coterminal, have the same. And remember, if you want to find other coterminal angles, either keep adding 2 pi or keep subtracting 2 pi from the result. Okay. Last thing, let's talk about this idea of arc length. Let's start right here. So we said above, let's go back to up here. We said that if the definition of a radian, we said that if you had some circle, the radius r with a central angle coming from the center, and if you go the distance, or this, we call this length along the circular path, s is equal to r, then theta is called 1 radian. Okay. So what we have, okay, let's draw a circle the best I can. Here's our central angle. Here's our radius r. So we go any distance, okay, any theta, okay, starting from essentially 0 degrees or 0 radians. Okay, in this case, 0 radians. Then this distance along the circle we go, that's called our S, our arc length. So if you move in a circular path through what's called an arc length. And the formula for that says this arc length is equal to r, the radius, times theta. Okay. Now, one thing here is it says theta has to be in radians when we do this. Okay, so theta's got to be in radians when we do this. Okay. So if you're given an angle that's in degrees, you have to convert it to radians. Okay. Now, here a formula, and this is kind of a formula has three variables, s, r, and t. As long as we know two of them, we can always find the third one. Okay, and we'll look at an example of each. Okay, so let's start here with one. Okay, for an angle theta is equal to let's do in radians. Let's do just pi over 2 radians, and r, our radius for a circle, is 3 feet. Okay, let's find s, find the arc length. Okay, it's kind of the simplest case, so just plug everything in. So we know theta, we know r, so that s is equal to r, which is 3, and then I'll put as feet, and theta, which is pi over 2. Okay, and also our arc length has the same units as the radius. So the radius is in feet, for example, arc length would be in feet. The radius is in meters, arc length would be in meters, and so forth. Okay, and so now if we just multiply this straight across, this is 3 pi over 2 feet, which is accurate, which is exact, but not all that useful. So let's actually do that on Desmos, approximate that, because obviously if we're going to use this, it looks like you're going to approximate it. So 3 pi over 2, 3, so pi, just divide it by 2, it's about 2 decimal places, 4.71 feet. Approximately 4.71 feet. Okay. Now, number 2. All right, let's say we have this time for theta is equal to 200 degrees. And let's say this time we know the arc length s is equal to 50 meters. Okay. Find r. Okay, so this time we want to find the radius. Okay, we know the arc length for the path along the circle. We know the angle. And one thing, hope you notice here, this is in degrees, so I have to convert that to radians. So let's first convert to radians, because if you do it the way it's written, if you do it, the formula will essentially interpret that as 200 radians, which is a lot different than 300 degrees. Okay, so we know how to do that. We learned how to do that then. 200 times degrees times pi. Since we want degrees to cancel out, we want degrees in the denominator. Okay, now let's just do this instead of exact, let's just approximate this because that's going to be more useful. So 200 times pi, pi, divided by 180, approximately, once again, to 2 decimal places, 3.49 radians. Okay, 3.49 radians. Okay, now that we have anything in radians, now we're ready. So a couple ways you can do this. You can just plug it in the formula if you want. Okay, so our formula is S equals R times theta. That's probably the easiest way. In this case, we know S, we know theta. Plug it in. Okay, so arc length is 50 meters, is equal to R times theta, which is 3.49. And so, just turn this around. That's a 5 there. Make sure that's clear. Doesn't look like an S. There we go. So R is going to be 50 over 3.49. Okay. Once you either use your calculator or Desmos, I'll just use the calculator in this case. So 50 divided by 3.49. I made a mistake. 50 divided by 3.49 is equal to 14, about 14 to 2 places, about 14.33. Okay, 14.33. Now, what are our units here? Well, once again, it has the units. S and R have the same unit, or R and S have the same unit. So this is in meters, so this is also in meters. Okay, let's do one more. Number 3, this time we know R is equal to 2.3 inches. S is equal to 17 inches. And then find theta. Okay. All right. So in this case, we have everything we need. All right. So S equals R theta. We'll plug everything in. S is 17 is equal to R, which is 23 times theta. Okay. S equals R theta. Of course, divide both sides by 23. And so this gives the theta is equal to 17 over 23. And I'll just do that on the calculator as well. 17 divided by 23 is equal to, I'm sorry, this is 2.3. Oops, I'm mistake. It's 2.3. Oh, yeah, I should get a bigger number. That's 2.3. Okay. So 17 divided by 2.3, and that's going to be approximately 7.39. Let's talk about what is that. So this is an angle. Now, so we said theta, when you plug the angle into the formula, it's got to be in radians. So when you get it out, this is going to be also in radians. It's 7.39 radians. Okay. Now, just for the sake of, let's convert that to degrees, just for the practice. Okay. And so 7.39 radians times, so to convert to degrees, we want the radians to cancel out. So we have pi radians down here over 180 degrees. We want the answer to be in degrees. Make it look like a better pi. There we go. And so let's just do that in Desmos. So 7.39 times 180 over pi. So 7.39 times 180 divided by pi, pi, and that's 423.42 places, 423.42. Approximately 423.42 degrees. So more than one trip around the circle. Okay. Now, let's do one more problem and one more thing that's a little bit conceptual. Okay. Let's talk about angular speed. And linear speed. Okay. So angular speed is essentially how fast. So angular speed is, so I didn't write that over here, but that's okay. Angular speed is how fast or instead of saying it this way, angular speed is speed, say it this way, having speed is how many radians I'll say covered per some unit of time. Okay, per some unit of time. All right, that's angular speed. Okay, now let's take a look at an example of that. Let's see, how am I? Okay, this is actually my last page. Let me just, to make sure I have enough, let me at least one more. We're good. Okay, what I mean by that is a good example of thinking about that is, for example, something familiar with revolutions per minute. So anytime I think about a wheel, okay, if you're familiar with engines, car engines, you have your RPMs on your car, revolutions per minute, how many times the crankshaft rotates per minute, for example, or any kind of revolution. Okay, a wheel goes through so many revolutions per minute or per second, whatever unit of time you want, even per hour. Okay. Now let's do a quick example of angular speed. Okay. Let's find angular speed for 20 revolutions per minute. Now just make it per second. Okay, 20 revolutions per second or minute, either way. Okay, so the idea of a wheel, okay, maybe the wheel is turning, all right, has some radius r, and of course some angle theta, and it's turning, maybe this, whichever direction you want, okay, maybe this direction, okay, 20 times per second, okay. So the question is this angle theta, okay, find how many angles per second that goes through in radians. That's what we're asking. How many, radians do we go through per second? Let me say this. So let's find the radians per second. Okay. Now, so one revolution, we know all the way around is 2 pi. So that's what we're going to use. One revolution around is 2 pi. So every time the wheel turns around, it's going through 2 pi radians. Okay. Now, the way to think about this is also essentially conversion. So we have 20 revolutions per second. We want our answer to be in radians per second, correct? Okay. So we want revolutions to cancel out. So I know one revolution is equal to 2 pi. So the question is it 2 pi over 1 or 1 over 2 pi? Well, the way to think about that, we want our answer to be in radians. Okay, that's 2 pi radians. We want revolutions to cancel out. So we want radians up here, revolutions down there. And so that's going to be 2 pi radians over 1 revolution. That's one way to keep track which way it needs to go. Okay, this equivalence. Revolutions cancel out. And that's going to be 40 pi. And once again, let's approximate that, since that's not the easiest way to think of it. So let's go back to Desmos really quickly. They say 40 times 3.14, basically. So 40 times pi, and that's 125.66. 125.66 radians per second. Okay. Now, if you want, you can also convert that to degrees per second if you want, the same way you did before. Okay. Multiply by 180 over pi. Okay. Now, let's talk about something called linear speed. Okay. Linear speed is the speed of an object moving in a circular path. Now, that can be either moving in a circle on its own or maybe like attached to a wheel. Okay. So think about here. And also, one more thing, this depends upon the radius. Okay. It depends upon the radius. So, what I mean by that, once again, here is our wheel radius. Okay. It's spinning in this direction, it's rotating. Okay. Now, let's say we have a point right here. Okay. Call that P1. And maybe down here, you have another point P2. Okay. Now, here's the interesting thing. They're both rotating. As they rotate, and they're essentially on this radial line. Okay. They're both. So the angular speed of P1 and P2 is the same. Okay. If they're both fixed to this wheel and they're on the same line, basically, then if you think about rotating, they're both rotating at the same angular speed, meaning they're both covering the same number of degrees or radians in 1 second, 1 minute, whatever. Okay. But the linear speed of P1 is greater. Okay. The linear speed, and actually, I realize this is, let me erase this and write this better. I apologize. I was out of practice writing with this. The linear speed is the speed of an object. Okay. Actually, the linear speed is greater because think about it's covering a larger distance in the same amount of time. For example, think about a minute. If these things rotate for a minute, they're going through the same angle in that minute. But since P is further out in the circle, it's be covering a greater distance in that same amount of time than P1. Okay. Now, how do we find that linear speed? Well, let's look at another example. Okay. So let's say, and call this number 1 or maybe number 2. Doesn't matter. Okay. Find the linear speed of a point on a wheel at a radius of, let's say, 2 feet and a radius of 3 feet. Or let's make it 4 feet, make it double. Okay. Feet. Both moving at 3 radians per minute. Okay. So to find the linear speed of these 2 points, speed of a point on a wheel at a radius of 2 feet and a radius of 4 feet, both moving at 3 radians per minute. Okay. We got a wheel that's rotating. All right. Now let's make it going this direction. Okay. That's rotating 3 radians per minute. Now I'm just going that direction so to be consistent with idea of positive. Okay. Of course, you can also go in the other direction. Now let's say I have a point, and let's say this is halfway. This is 2 feet, and this one is 4. Let's say the wheel is 4 feet in diameter. 4 feet. Okay. How do we do that? Well, what we know is since we're going to use S equals R theta, okay, here with, or make it theta over, well, I think it's often called omega, okay, with omega is equal to theta, or angle, per time. Okay, what does that mean? So same formula, all we're doing is essentially dividing our angle by time. So find the speed, sorry, I need to change this too, so let's make this, let me start over. I didn't do this at first, okay. Let me say this, so from S equals R theta, okay, start from that point, okay, okay, divide them both by time, okay, we divide them both by time, S and theta by time, then let's call this V equals S over time. This is our linear speed, okay, velocity, V for velocity, okay, and then theta, or let's call it omega. I think a lot of times you can call it omega, small Greek letter omega, so kind of like a W, is equal to theta over time. This is the angular speed. So basically use the same form, okay? V equals R times omega, okay? And now let's plug these in, okay? For R equals 2 feet, okay? This is going to be V is equal to 2 times, there's 3 radians per minute. Of course, that's going to be back up. So it's going to be specifically 2 feet. Okay. Now, what's also, since this is a linear speed, this is going to be in, for example, something like feet per minute, meters per minute, something like that, distance per minute. Okay. And so this is going to be 6. 2 times 3 is 6 feet per minute. Okay. Now, let's also do the other one. 4 r equals 4 feet distance. Okay. So if we look here, for that we're twice as far out, let's see what that effect that has. We know it's going to be faster because you're covering a greater distance in the same amount of time. For example, one revolution, they both cover 2 pi radians, but this one covers a greater distance because it's further away from the center. Let's see what that does. Okay. So for 4 feet, it's going to be exactly the same, except replace the 2 with 4. So 4 feet times 3 radians per minute. And that's going to be 12 feet per minute, actually twice as fast. So if the distance is twice as far from the center, you have the same angular speed, your linear speed is twice as fast. Okay, or another way to think, this is half the speed. 2 feet is half the speed of 4 feet. Okay, let's see what we've learned today. So what we learned about radians, what a radian is, and how you can use radians to measure angles instead of degrees. Okay, learned how to convert from radians to degrees and back to radians. You learned about the arc length formula, learned how to use it, learned that the S equals R times theta, where theta is in radians, learned how, as long as you know 2 of those variables, you always find the third one. Then we also learned about linear speed and angular speed and how to use those. Thank you. Have a good day.